Hello there, my name is Tim Severs. We will be doing Module 7 now of the ICAT training. We're going to be talking about asphalt plants and the calibrations that we need to do to make sure they perform correctly. Kind of a brief history of my experience. I've started with bricks construction back in 1978, so this will be my 43rd season. Started off just as a laborer and then kind of got sent out to the plants to help out, and it was probably a good time because that's when the plants first started changing from what the old style was, the old batch plants, and then through all the modernization and automation and computerization, I kind of grew up with it. So I got a good learning curve for me. So you've been in the labs, you've seen how they put asphalt mixes together, designs, and in the real world, 8-hour day, you're going to put together a little over 100 pounds of material and come up with the design and say, great, here we go. Now we're going to hand this recipe off to the plants and say, here, can you make this for us? But the problem with it is, at the plants, you're going to make it 50,000 to 100,000 times faster than what you do in a lab. And it gets really complicated. And this is where the inspection and the calibrations come in on your plants. In a drum plant, proportioning is accomplished by moving weight system. The computer monitors must be checked for accuracy. By moving weight system, rather than batching things out, we have scale conveyors where the material is just going up a conveyor belt and we're weighing it continuously. The load cell in each aggregate belt must be checked by running material across the load cell into a tiered trucks, which means we know the weight of an empty truck. The computer inventory must match an actual weight by 0.5%. Everything at the asphalt plants in calibration mode has to be within 0.5%. 3 consecutive times. Everything you calibrate, 3 consecutive times 0.5%. And you need to do these quite frequently, once a month, or just whenever things just don't seem like they're working out right. At the beginning of each season, you also have to check your asphalt pumps and make sure they're correct. The binder check, you can either use a tiered distributor, which is the tank truck, or you can use a portable tank sitting on load cells. What you'll do is you'll get all your asphalt flowing well, you will tell it to start injecting asphalt into the distributor or into the tank. And then when you shut it off, you'll check the amount that the computer thinks it put in the tank and what you actually put in the tank by reading the scale readings. There again, 0.5%, 3 consecutive times. The fines return system also needs to be checked. Will be the fines coming out of the bag house. You have to meter back in. There's a way to do that. You have to do it within 0.5%. When you're doing all these asphalt scales and aggregate scales and meters, you should do it at the maximum. If not the maximum, at least in the range where you're going to be utilizing them constantly. The allowable difference between the scale reading and the actual weight applied shall be 0.5% or less throughout the range. Meter variation, there again, 0.5%. All right, I'm going to show you some examples of how this gets accomplished, and you figure out what your percent error is. On this particular example, the dump truck, when it was empty, weighed 36,700 pounds. Once they got done putting material into the truck, it weighed 79,140 pounds for a gross of 42,720 pounds on the first example there. So the net weight would be the amount that the truck weighed full minus the tare weight or the empty weight. And there it is, 79,140 minus 36,700, 42,440 pounds. The computer came up with 42,720 pounds. So therefore, the next calculation will be, in determining your error, you'll always take the net computer, what the computer thinks it put into the truck up the conveyor. And in this particular example, the computer thought it put 42,720 pounds into the truck. And there's the example. To do the percent error, you take your known weight, which is the 42,440 pounds, because that's how much we determined of the material we put in the truck. The variable weight would be what the computer thinks it put in the truck. You do the percent or the pounds difference, 42,440 minus 42,720 times 100, 280 pound difference versus the actual weight. You always take the difference divided by the actual weight, and a 0.0066 or a 0.66% error. Now, not bad, first try of the season. You're close. You can either, at this point, do calculations and figure out how to adjust your span values in your electronic scale conveyor, or most of them anymore, you just tell it what the error is, the pounds error is, and it will do an automatic recalibration. So, you're off on the first one. Let's go again. Did it 3 more times. And as you can see here, use the same tare weight every time for the truck, 36,700 pounds. In the gross computer, they kept accumulating, so you had to go down to where the net computer is and see how much the computer actually thought it put in. The second line there, gross weight of the truck, 81,040 pounds, minus the tare, equals 44,340. The computer thought that time, when they ran the material up the belt into the truck, they put in 44,490, which is a difference of 150 pounds. So 150 divided by 44,340 is a 0.34 error. Congratulations, you're within tolerance. Now, you can either not adjust the computer at this time, or if you think you can get a little closer, okay, go ahead and do a calibration. Let it change its spans numbers to get it a little closer. Now you can see it. In the next two, they did it both times. They got down to a 0.3 error and a 0.17 error. Now, same thing with the asphalt. Gross weight and tare weights. They did it 3 times in a row here. The tare weight changed. Okay, you're using a distributor, you put liquid in it, and you pump it back out every time when you get done. So it's not going to exactly weigh the same thing. And it's probably not a bad thing even when you're doing the dump truck, checking the scale conveyor, to do it the same way. Sometimes some of the material get hung up in the corners of the dump truck, or when they dump, some dirt will fall off the bottom, whatever. Best case scenario, always check your tare weight every time you do this, because you're trying to get within 0.5% error. And when you're only doing like asphalt meter checks, that's 20-pound error is about all you're allowed. So in this one, you've got 3 computer weights, you got your 3 gross weights, 3 tare weights. The first one there is a net weight of 4,880. The computer said 4,890, only a 10-pound error, which gets you the same calculation. Known weight minus the variable weight or the computer weight divided by the known weight 10-pound air divided by 4,880 pounds calculates out to a 0.2% error. Right on the money. And there's the other two calculations. 0.41% error, 0.21. So, a lot of numbers, really not all that complicated. You figure out how much material you put into a truck, or how much material or liquid you put into a tank, compare it to what the computer thought it did through the process, the pounds different divided by the pounds actual, gives you your percent error. Okay, now we're going to get into the componentry of the plants. When you put the mix design together in the lab, you may have used 3 or 4 different aggregates. So basically all plants have at least 4 cold feeds. This particular instance here, there's 8. 10's great. It depends on how many different aggregate sources you're utilizing. This is the gathering conveyor coming out from underneath all the cold feed bins, going up to what they call a screen deck. In this case, you're really not sorting material. That screen deck up there is just to keep any large particles, oversized particles, or things like that out of your mix. It's amazing sometimes what'll come off these screen decks. We've had dead raccoons, we've had deer, you name it. Mostly comes out of places where there's natural sand to get into the piles and get buried. All right, this is an aggregate feeder, belt feeder. You have different size gate openings if you want. The motors on these are controlled variable speed through the plant computer system. There's a little paddle hanging down there that has a mercury switch in it, which is a no-flow switch, which will notify the plant operator that there's no material coming out if that bin would happen to go empty. So it's just an indication to shut down and wait for the loader man to get caught up. This conveyor here is the scale conveyor. You can see the screen on the side there where the stuff comes out of the cold feed bin up across the screen deck and down on the scale conveyor. Up halfway up this conveyor, where the sides are, is where the load cell is. One of these troughing rollers underneath this conveyor belt is actually sitting on a scale, sitting on a load cell. So as all this material is going across it, the computer system is weighing it. There's also on this conveyor a signal generator that gives us a basis of time, because you can't use real time, because sometimes these conveyors, as you put more of a load on them, you're running heavy, they'll slow down a little bit or speed up a little bit when you slow down the plant. So we actually use a speed indicator on the conveyor belt itself so we can take the weight versus the time to do a ton per hour calculation. This is all done within the computer on the control system on the plant. And there's an old photo of a control system. You can see on the panel there at the left, that's your 8 cold feed controls. There's an old deck printer there and control systems on the front panel there. And there's an overhead of that whole setup. Cold feed bins on the right. The first conveyor is just the gathering conveyor, all the material coming out at the right speed, right combination, going up onto the screen deck, dropping down through there, get all the garbage out of it, onto the scale conveyor, and then going directly into the drum. This happens to be an Aztec double barrel drum. There's all different ways. There's too many different ways to try and explain to you how it works. The main thing is the inside of these drums, if you've ever looked in and seen a dryer, clothes dryer running, it's the exact same thing. There's a burner on one end of it. Some of them 100 million BTU an hour, burning lots of gas, fuel, waste fuel. They've experimented with pulverized coal. Anything that'll burn, they burn them through these plants. Take these aggregates with the internal moisture they have in them, you run them into the plant. The heat from the burner heats these up to the 350 degrees range to create the mix by taking all the internal moisture out of the aggregate. Kind of a quick number just to make you understand of how this process works. A general rule is for 1 ton of aggregate, it takes 300,000 BTUs to raise 1 ton of aggregate from ambient temperature up to the 300 degrees. There's a picture from the other side of the cold feed bins with the front end loader taking the material out of the stockpile and putting it into each separate bin. Good separation. You don't want cross contamination from one side of the bins to the other. There's another picture of the conveyors. You can see everything in the drum on the left. Now, right behind the conveyors there is the bag house. So you take this 200, 400 ton an hour aggregate going through this drum and you're heating it up, major airstream. You're creating a lot of dust. Now you can't put this dust into the air. The bag house is nothing other than a huge self-cleaning air filter. The exhaust fan pulls the air through, is putting clean air out the stack. Those stacks have to actually be tested once every 5 years, in some instances more than that. Now the dust that comes out of the bag house goes right back into the mix. Sometimes you put it all back in, sometimes you don't. That gets back to where we were talking about calibrating the dust return system. Different view, these are the wrap feeders putting wrap into the other end of the drum where it mixes with the high virgin aggregate. The dust silo on the left there with a conveyor, screw conveyor, taking dust up into the drum, returning it back to the mix. The 3 large round things are just storage silos. Completed mix goes up the drag slat, the big square thing, it's just nothing more than exactly what it is, a drag slat. The mix comes out of the drum into the boot of that thing, big chains with slats on it. It just drags the material up and you deposit it into the correct silo. There's a different drum, more of an older style drum. It's actually dropping into a secondary drum where the wrap is introduced outside of the one drum, so the wrap in the asphalt is not subjected to the hot airflow. Here's another one. They call this a zone drum. This is the counterflow. Material stuff goes in the high end going down, wraps at it halfway. Another view of the drag slat. When you start to stop, there's a hole in the bottom of them on a door that just drops open, so all the material that's not quite right as far as good spec mix is dropped into a truck and put on a spoil pile to be processed and reused again. More silos. And another bag house. Nothing other than a great big self-cleaning air filter. Dust silo. So all the dust comes out the bottom of the bag house. It's augured or blown into these dust silos. And then at the bottom of them is a rotary airlock where you just meter back in what you need. All the conveyors move the dust. There's one there coming out, doesn't have anything on it. That's in case you need to empty the bag house or you need to waste it.